Okay, as usual, I'm going to record every sections of my lecture here. So in case I forgot to do the recording, please you guys remind me to do the recording for it. All right. So please remind me to do the recording if you notice that I didn't record the lecture. Yeah. So you may see this notice. Yeah. All right. So it's recording now. Okay, good. Okay, one by one. So, okay, so I think maybe this one first. Yeah, I know it's a little bit silly over here, but sorry, that's the regulations. Please, during these sections from 6 to 9:30, okay, please drop by your spectrums and take your attendance over here. Okay, please stop by your spectrum and take your attendance over here in between 6 to 9:30. So you have plenty of time to do this. Okay, but don't forget to do it, right? Okay. As usual, so after I've done the recording, so all my lecture, I think you guys probably know this. So we'll be go into the channel of this SQB704. So that will be in this general. So that will be appear over here. Okay, you may go and get the download or view the video in this folder file, right? Okay, so that's a general thing. Right, so let's go to this thing first. Okay, so number one. All right, this thing I have already uploaded to the spectrums. Okay, so you can get this information. So first one will be the cost pro forma. So yeah, you can see here. So it's briefly discuss the synopsis for the course. So at least you have some idea. The content or the topic that we're going to discuss in this course. Yeah. So as usual, I think you guys probably knows already. So the continuous assessment is 50% and the final examination is 50%. Okay. So you may get, I think this is the important informations in this file. So the synopsis for the course. No textbook. Okay. So this is the first official documents. Okay. So the next one will be this, the current informations. Okay. So maybe you can look at this. So here list down some of the recommended textbook for this course. Okay. Maybe I will let you know. Most of my, or not all, okay, most of my teaching material are get from this book, Alan Carr, Probability Theory. Yeah. There is a hard copy in our library. Okay, but I think all of you not going to drop by to your campus. Okay. So you might go and get this one. Okay. So there are also other references. Okay, Ross and so on. Yeah, you may get this thing. All right. So next one will be this. So this is my original plan for the assessment of the course. So as I said just now, so the continuous assessment will be 50%, whereas the another 50% will be for the final examinations. Okay. Okay. Because there might be some change of the regulation for the the format for the final exam, which I can't tell you now because I haven't get the what they call it, the final notice from the faculty. Yeah, so that's why I also not sure how's the format for this final examination. So I will update you later. Okay. And because of this, so I might need to do some changes of my plan here. Okay, according to my original plan will be this. So I'm going to split this continuous assessment 50% into 3 parts. So 2 assignments, 10%, 20%, and another 20% for the test. So my original plan was assignment. So the deadline will be the submission deadline will be 3rd of December, so which is actually in week 7. Okay. And for assignment 2, this is actually my original plan will be week 12. Okay. So whereas for the test, so I'm going to, this is my original plan, so it's supposed to be on week 14. Okay. And as I said, I still don't know what is the format for the final exam, because according to my original plan, so this one will be on week 16 or 17. Okay, that means 16 or 17. Okay, however, it seems that there might be a change for this thing. So this one possible in week 14. Okay, I'm not sure about this. Okay, put question mark here. So because of this uncertainty, I think maybe I'm going to revise the date for the test. Okay, so that's why I'm going to change this. Yeah, it doesn't really matter. So the test, so I'm going to put it over here. So the test, so as usual, that will be again 20%. The proportion will be the same. So the time is still the same, 6 to 7 p.m. So the only difference will be I'm going to put it to 12. Oh, sorry, not 12. 17th of December. So this is actually in week 9. Okay, anyway, I'm going to, I think I'm going to put it in this way. So week 7 will be the deadline for assignment 1. For assignment 2, week 12. Okay, so 7 to 9, there are 2 weeks gaps for preparing for a test, should be okay. And after that, 3 weeks for the preparation for your assignment 2. Okay, so I think the gap should be okay, right? So for the final exam, so not sure, so to be announced. Okay, I will update you guys later whether I'm going to put it in week 14 as a bring home assignment or written examinations, online examination in week 16 or 17. So I will let you know later. Okay. So that is the assessment method for this course. Okay. Any questions? Okay. One more. Okay, I have one more request from you guys. Okay, so as you guys can see, most of the time I'm going to display a screen like this. So which means I can't see your message over here. Yeah. So please, if you have any questions, please voice up. Yeah, just voice up. Don't just type a message over here because I can't see it. Yeah, most of the time. Yeah. So you have any question, please voice up instead of type it over here, right? Okay, so that is the thing, some notice for the assessment for this course. Okay. Right. Okay, so that's it for this. Okay, next will be this. So as for all the courses, okay, I think this is the last one among all the courses that you have attended for this week. Okay, so this Friday. So I believe you all know this. So for our class, for our, I don't want to say lecture, for our class will be from 6 p.m. and then run up to 9:30 p.m. Okay, 3.5 hours. Okay, I'm going to do it in this way. So I'm going to split this 3.5 hours into 3 sections. Okay, first, that will be starting from 6 p.m. and then up to around, okay, sorry, I'm a bit lazy. So I would say 7:15 p.m. plus. Okay. So it might be up to, okay, plus, okay, around this. So 1 hour, 15 minutes, or maybe 1 hour, 1.5 hours. Yeah, so this is the first section for the lecture. Yeah, section 1 for the lecture. And after that, I'm going to give you guys a break. So 7:30 to 8 p.m. So a break of half an hour. But as I said, usually it will be some extra 5 minutes or 10 minutes. Yeah, because it depends on the progress here. Yeah, so I try not to reach up to 7:30. Okay, I will start early. And after that, so we have our second section for our lecture, 8:30. Oh, sorry, 8 until again. So I don't want to fix the time. So that will be a 9:15 plus. Okay, but definitely not more than 9:30. Okay, so this is the second section for a lecture. So approximately, my lecture will be sort of like, so maybe I would say 1 hour, 25 minutes. Okay, 1 hour plus another 1 hour, 25 minutes. So it's around 2 hours and 50 minutes around. Okay, so roughly like that. Okay, so that is how I'm going to conduct the lectures over here. Okay. Okay, so you have any comment with this setting? I believe okay, right? Okay, so as usual, silent. I will assume everything. Everybody agree with this. Okay. Okay. Next things. That will be the discussion for our tutorial questions. Since we make once per week, okay, so our tutorial section will be put together over here. Since we only have one group over here, so that will be quite easy, and it can be quite flexible for us to arrange the tutorial sections. Okay, so I'm not going to fix the tutorial sections, but roughly like that. So maybe we have all together 14 weeks, right? Okay, maybe week 3 or week 4. Okay, depends on the progress of my lecture. So I'm going to start the first tutorial 1. Okay, and so on. So most usually, maybe I'm going to spend 2 weeks for one tutorial paper. Okay, so 2 weeks. I have all together 5 tutorials, so that means it's about 10 weeks for 5 tutorial papers. Okay, so that's why I begin with 14. So then up to week 4, up to around week 14. So we should be able to finish it. Okay. So 2 weeks, something like that. Okay, so this is for the tutorial section. All right, as I said, since we have only one group here, so it can be quite flexible. Okay, so we can always do some rearrangement for the tutorial sections for the course. Okay. Okay. That's it for our general information about the course. Okay, so yeah.
Sorry,
Yes.
just a question on the tutorial.
All right.
Are we expected to have finished the attempt the problem before we come to the tutorial, or are we finishing the problem together with you during the tutorial?
Okay. How should I say? Okay, so I'm not going to expect you guys to have any presentations or what regarding to the tutorial questions. Okay. But I hope that you guys will try to solve the tutorial question first before come to the tutorial sections. Okay, so maybe my usual practice will be like this. I hope you guys can give a shot first. You try to do the questions. Okay, so if you have any problems with that tutorial question, so you let me know in advance. Okay, so we're going to focus on those questions during the tutorial sections. All right?
All right.
Yeah. It's not compulsory for you guys. Come on, you are all grown-up people, right? You are not small kids, so I'm not going to force you guys to do the homework. Okay, so you guys, but I expect you will try to solve the exercise first, the tutorial questions. Okay. So in case you have any issues, so you let me know. I will focus on those questions and discuss. If I receive no comment on it, okay, so maybe I will just pick some of the which I think important and challenging question to discuss during the tutorial sections. All right?
Okay. All right.
Okay. Yeah. Okay. No problem. Yeah. Anything else? No. Okay. But can I see how many attendants? How many members? 11. Okay. Never mind. I suppose all of you are here. Okay. Good. So that's the thing. Anyway. Yeah. Come back to this again. So I think okay, right? This one. The important date will be this week 7. Week 12 for assignment 1, assignment 2, okay, and week 9 for your test. So the scope for the test, I'm going to let you guys know later, okay, and of course, and the assignment 1 and assignment 2 will be uploaded to the Spectrum later, okay. So, okay, I'm going to update this date and then post it to the Spectrum later, right? Okay, anything else? Okay, no, that's it. Good. So, okay, are you ready? So then we are straight to the lecture, right? Okay. Okay, I'm not sure whether you, I don't know how much you know about this course, okay? Also, how much you know about this topic, okay? Maybe this is a SQB7004, so-called probability theory, okay? Okay, so I can tell you this paper is very much different from the other paper that you have attended or you're going to attend in this course. Okay, so in a way, this paper is a theoretical paper. Okay, it's a very theory. Yeah, it's about theory, and not only that. On top of that, so this is more on mathematics. Okay, rather than statistics. Okay, in fact, I don't know your background in mathematics. So what I can tell you is this one is a topic in mathematics. To be more precise, so this is a topic in what we so call real analysis. Okay, topic in we can say a subtopic in real analysis. Okay, in a way, it's a theory, so it's a kind of abstract papers. Okay, so it's not like other subject that you have or you're going to attend in the course, so which emphasis on more towards to the applications of the thing, the formula and so. Okay, however, this one are not the different. Okay, so this will to discuss about the formulation of this probability theory and statistics. The underlying formulations of these things. Okay, so that's why it will be very much fun. It will be a very mathematical approach. Okay, so please get ready for it. Okay, so I have altogether 6 chapters. Okay, So I prepare a 6th chapter. So this is okay. So this is chapter 0. Okay. So chapter 0. So it's sort of like I will gather all the necessary those mathematics for the course. Okay, I will try to gather all the important mathematics tools, I would say. Okay, for the course. Okay, so and after that, chapter 1 and so on. So we will start to discuss the main topics of the course, the probability, random variable, and so on. Okay, so here I'm going to do a revisions on some of the mathematical tools that you have learned before, as well as some of the new concept in mathematics that you haven't learned before. Okay, possibly. Okay. So okay, let's start with this. Okay, I suppose you guys have learned the set theory before, and you guys are familiar with some of the standard notation in set theory. Okay, hopefully. So one thing. So this is a first thing that we're going to do is a complement. Okay, so AC. So if we given a set A, so the complement of A will be all the elements or all the object which does not belongs to A. Okay. So I think you get this right. Okay, so if we have a two set A and B, we have a union of them. So I suppose you have learned this before. Okay. Complement. So union. Okay. Okay. Then we also have this. So we also have intersections. And this one. Okay, I assume you know this. Okay, difference. Okay, that's the way. Okay, so maybe make it easy. So for example, number 1, let's say this is the whole thing, the universal set. Okay, so this is A. Okay, so if this is A, so the inside is if the one circle is A, so the complement will be this. Okay, everything which is not inside A, so the A complement. So and secondly, so again, if we have a universal set, so let's say we have this A, this B. Okay, so let's say this is our A, this is our B. Okay, so the union of A of B will be this. Okay, A or B. So we are putting all the A and B. And also, so again, if this is A, this is B, so this is A and B. So then we have this is A or B, and this is A and B. Okay, so I believe you guys have seen this before. And number 3, okay, maybe this is something new. So it's still the same. So we look at the same diagram. So again, supposing we have A, we have a B. So this is our A, this is our B. Okay, so the difference between A and B, so we just put the notation A minus B. Okay. So A minus B will be all the object which is in A but not in B. Okay, so which means in A, okay, not in B. So that's the picture for it. Okay. So again, I believe you have seen all this. Okay, in general, so if you can see for item 2 and item 3, so we discussed only two sets, AB, AB, and AB here. Okay, in particular, the union of AB and the intersection of AB, so we can extend the idea to more than two sets. Okay, so in general, we have this. If you have a class of set, okay, we just put a script alphabet A. So that means we have a collection of A, lambda. Lambda belongs to index set. So we can talk about the union of this, of them, as well as we can talk about the intersection of the class. Okay, maybe before this, need to briefly explain the meaning of this so-called class. Okay. So the rough idea, you know, when we talk about set, so a set is like a set is like a collection of certain object, right? Right, a set is a collection of certain objects. So this object could be anything. So we have an example. We can say the set of all even numbers. Okay, so that is a set, correct? So that is a set of 2, 4, 6, and so on. And we can also have a set of all fruits. Okay, so that will be, we can have apple, okay, durian, and so on, right? So as you can see, a set, those thing inside, it's not necessarily number. It can be any kind of the thing, object inside, right? Okay, the idea will be here. Since we are talking about objects here, so this object could be set. Okay, so that means then we can talk about this. A collection of certain sets. So then a set of sets. So if you're using set, that will be a bit confusing. So therefore, we use a new term, so-called a class, which is just to distinguish between set and class, a collection of certain sets. Okay, just to let you know, distinguish this. Okay, because in our, okay, I think this is the one. So a class, just to let you know, we just said that the element for class is set. Okay, that's it. And usually when we class, we're going to use the script, what do you call it? It's a landing symbol to describe a class. So for example, we will use A, B, this, and so on, okay, to denote a class. Right, so that's the meaning of class here, okay. Okay, now supposing we have a class of set, script A. So A lambda, lambda belongs to an interset, capital lambda. So for examples, we can have this. So we can have an example. So let's say we can say this one to be A1, A2, A3, A4, A5, and so on. Okay, we have we could up to have infinite many of them. So we can say this is A lambda. Lambda belongs to the set of all natural number. Okay, so that means this is this. So in this example, then we can have this. We can have a class of set which contain more than two. In fact, it can be up to infinitely many of them set. So we can also talk about the union. So that means in this case, then we can have a union of lambda belongs to n A lambda. So that's actually A1 union A2 union A3 and so on and up to infinity. So similarly, we can talk about the intersections of this case. So that will be A1 up to A2 and A3 and up to infinity. Okay. Okay, so this intercept here could be any kind of set. However, most of the time we will take this lambda to be the set of all natural numbers. So we can extend the idea for union and intersection up to infinitely many of sets. So this is the way we're going to denote it. Okay. Okay, next we have two important formulas here, so-called the De Morgan's formula. So I believe you guys have should have seen this before, right? So the complement of A and B will be the complement of A or complement of B. Okay. The complement of A or B will be the complement of A and complement of B here. So again, maybe I think just give you a picture for it so that you get a very easy idea for it here. Okay. So let's say again, so we're going to have a, let's say we have A here, and we have a B here. I think not good idea. Okay, so let's say this is our A and B. A and B. Okay, so if we look at A and B, so that will be inside here. So this is our A and B, right? So the red color will be A and B. So if you take the complement for A and B, so that will be everything that's outside here. All the parts, excluding the red color portion. Okay, excluding the red color portion. So this will be the complement for it. So as you can see, that will be everything except here. So we look at another diagram. So again, so this is A and B. Okay, now we look at here. So the complement of A will be this, the red color. So this is our A. So then if you look at the complement of A, so that will be this. Okay, so excluding A. And if you take the complement of B, so that will be here. Oh, you can see difference. Red color. Okay, so you can see, maybe you can take this. So we can take a label for this. You label all this. So we have labeled all the part except the hole in between. So that means without this. So you can see, so then it end up to be, these two are the same. Okay, so from here we have A or B. So this and this are identical. So this is what we so-called a De Morgan's formula. Okay. So again, in general, we can actually apply a general formula to the De Morgan's law. So that will be this. Okay, you just have to remember this. First of all, you have intersections. Okay. And then you have a set A here, lambda. Okay. So once you apply the complement, okay, so then what you can do is, so you just have to change this intersection to unions, and after that you just have to bring the complement inside. Okay, you just have to upside down this and then bring it inside. So similarly, you can do the same transformation of this symbol. So again, supposing we have an original, we have this. So if we are taking the complement for this thing, so what you can do is, so the union, you will put it upside down, so it becomes intersections, and then you just put the complement inside. Okay, from outside, put inside. Okay, and then change the intersection to union. So that's the way. Okay, so next one, I think we have already, I have already discussed this. So this is our conventions. So as I mentioned just now, most of time, so in most cases, we're going to take this lambda to be n. Okay, so in this case, then we're going to use this notation. Union of small n belongs to this set of all natural to be n rounding from 1 to infinity. So that's the way we so we can either use this or use this notation, up to you. Next will be this one. Okay, so this is a very interesting picture over here. Yeah. Okay, this is very interesting. So you just take note for this. Okay, maybe I put C. Yeah? So this A, B. So if you have union, intersection. So if you intersect, so here we have only finitely many. Okay, if you do the intersection of finitely many of them, so the open or closed interval thing, so will not be changed. So this one will remain the same. It must be closed at the end. Okay, it will be the same. So similarly, if you have a union, if you take only finitely many union, open, so it's remain open. Open thing. So even if you take the closed things, forget it. So similarly, if you take the intersection for a closed interval, if you take only finitely many, okay, I think, wait, okay, doesn't matter. We don't worry about this one. Okay, I think maybe this one I should put closer. Okay, so if you take finitely many, so it doesn't matter. It won't alter the shape for the interval. Okay, it will be close to close, open to open, closer. So even if you take this one, so the close one will be remain a close one. So even this is finite intersection. So similarly, if you take union, finite union for closed interval, so it will remain the shape of close. Okay. So this is okay. So close, remain closed, open, remain open. So when you deal with finite cases, doesn't matter. So you don't have to worry about the shape of the interval, whether it's open or closed. However, when you do the intersection or union, okay, anything? Oh, okay. Okay, never mind. Let me finish this thing first. I'll come back to you. So this is the case when you consider finite union or finite intersection. So don't worry about the shape of the interval. However, when you come to the up to infinity, then you have to be very careful. Okay. When you do up to infinity, so for example, you can this will become closed already. So I just look at the examples. I think maybe we look at this example is good enough. So look at this example. So we are talking about this set minus 1 over n minus 1. So I think you can see right here, this is open. So here we have open interval, right? So what happens if we take the intersections n running from 1 to infinity? So you can see the answer is if we take an intersection of infinitely many of open set, it will turns out to be a closed set. Okay, so we can do it easily. So we look at this interval. What we can do is we can just check one by one. So when n is 1, what do we have? So when n is 1, so you substitute n is 1 here, we actually have minus 2 up to 1. Right? We have this. If we take n is 2, what do we have? So if the n is 2, right? So it turns out to be minus 1.5 up to 0.5. Okay, it still remain open. So we go further. If we take n equals to 3, so what do we have? So 1 over 3 will be 0.33, so it's around minus 1.33, and then here will be 0.33, right? Maybe you take one more, then you can see. So minus 1.25 and then up to 0.25 and so on. You can go proceed. Okay, you can look at here. Okay, supposing this is minus 2, this is 1, right? Okay, first of all, when n is 1, we are running from here up to here. Okay, so this is open, right? So that means we're actually excluding the 2 endpoint. Okay, and we get all of them. Okay, so we fill up the whole line and excluding the 2 endpoint. Okay? Okay, next, when n equals to 2, it turns out to be minus 1.5 to 0.5. So which means it will be somewhere here. Okay, so 0.2. So this is minus 1.5, and then we are up to here. So you get a smaller. Okay. Then you can see where is our minus 1. So for example, we can see this is 2. So let's say this is our, just for example, just make it easy. So let's say this is our minus. So this is our minus 1, and this is our 0. So you can see minus 1, 0 inside. So which is still inside here. And next, if you do further, minus 1.33, so it will be somewhere here. 0.33, so this 0.5 to get it closer to 0. Okay, so you can see the red color portion, which is still inside. Okay, it still remains. And if you go further, minus 1.25, so it's somewhere here. It's even smaller, so this is also a smaller one. Yet this is minus 1 to 0, which is still inside. So if you keep going, so you can see minus 1 and 0 always included inside. Although in all this line, the two endpoints are not included. Okay, so if you take up to infinity, at the end of the day, this minus 1 and 0 will be always belongs to all the line. So that's why this is always belongs to here. And you're getting closer and closer to it. So if you take the intersection, that will be open to close. Okay, so you have to be take note for these things.
Sorry, sir, can I ask something?
Yeah, sure.
Yeah, I wanted to ask this intersection, right? Is it intersection of two different classes for the two things within the open interval?
I don't understand. No, actually, is this is one class. Okay, a class of open set.
So it's like a set of coordinates, is it?
No, it's a set of set. Okay.
Set.
Okay, I have a class. Okay, it's like that. So actually, it's like we have a script A. So this is a class. So the elements inside, the first element is the interval minus 2 to 1. Okay, this is the first element.
Okay.
And the second element will be this minus 1.5 to 0.5. And the third element will be minus 0.33 and so on, 0.33. Okay, and so on. Get it?
Yeah.
So that is it. As I
okay.
say, you get a picture?
Yeah,
so,
I got it.
Right.
And the closed interval, it means that it includes the minus
And-
1 and negative 1 and 0 as well, is it?
Yes.
Okay.
Okay.
Okay, thank you.
Okay, no problem. Again, that's the issue here. So I don't know your background of the mathematics. Okay, so I assume you have learned all this in at least in your bachelor degree or in your high school things, huh? So I believe this one is a kind of standard, right? So for example, open, maybe just a review, very quick. Okay. So we talk about open interval. Okay, so that means we are exclude the two endpoint. Okay, open means we exclude the two endpoint. So example, we use this notation 0 to 1. So that means without 0 and without 1. Okay, we put like this. Okay, so excluding 0 and 1. So this is a open interval. And we talk about closed interval. So we are going to include both endpoint. Okay, so that means. So of course we also have an open. Okay, so this one, so that will be 0 to 1. We use this notation. Okay, of course we also have an open, close interval. Okay, so that will be like this. Sorry, open, close, right? So we have basically we have how many types? 4 types, right? Open, close. Okay, so we also have a close, open interval. So example 0 to 1. Okay, so this okay, 4 types of these things, eh? Okay, so that's an example. So this is excluding. So the mean this one is we include 0 to 1. So for this, right? So we exclude 0, but we include 1. So 0 is included, but 1 is excluded. Okay, so we have 4 different kind of the interval, right? So I would say this is the nature for the interval. So what I'm trying to tell you is, with this. So when you take a finite intersection of finite unions, okay, it won't alter the nature of the interval. Okay, I just put it here. So finite intersections or union will not change can I say nature? Okay. Okay, I'm running out of space. Okay, borrow a little bit. Will not change the nature of the interval. Okay. So that's the. So this is what I'm trying to tell you. So you can take finite, when you take finitely many of the set, you take either intersection or union, so you don't have to worry about it. So it's always remain the same. It won't change it. It won't alter the nature of the interval. So however, when you go up to infinity, so you have to be careful. When you go up to infinity, so this is an example when this is open. So when you do intersection up to infinity, it might turn out to be a closed one. So this would end up to be this. Okay. Again, luckily, it won't be too complicated. You just look at these 4 patterns on it. Okay. So what you can do is you may assume this is 0, for example. So if you take the interval, you get things smaller and smaller from this side. So you take intersection, so it ends up to be a closed one. But this one, it doesn't matter. It will affect close to close. So that's the way for it. Okay, so this is another example. So we can verify easily. Okay. Okay, maybe just again, just to let you know, this is a class. So this is a set. So because interval is a set, okay, this is a set. So just to let you know again, a class is a group of set. Okay, so in future, whenever I mention class, so then immediately you think of it, element of class is a set. Okay, maybe I can put it in this way. A class is a group of set. Oh, how come we miss these 2 further? Okay, a class is a group of set, or the other way, or you can put it in this way, elements of a class are set. Just remember this. Okay, so we can do the similar calculation for this to get the answer. Okay, so the next one you can see this. So for example, if you look at it, similar calculation, negative infinity to 1 over n. If we take union for it, what happens to it? Okay, so you can see when you look at the first one, n is equal to 1, you can do the similar calculation. That will be negative infinity to 1. Okay, so when n is 2, so that will be negative infinity to 0.5, and so on. So when n is 3, you get negative infinity to 0.333, and so on, including. So again, as I said, you can see this. So just look at the line here. Of course, this is infinity. So this is from infinity and then up to 1x, including 1. So this is a negative infinity. This is negative infinity to 0. And let's say 1 is here. So you can see this. Okay, no, I think not 0. Okay, we can put 1 here. Okay, yeah, 0 is smaller than it, so 0 is here. So you can see this is always inside 0 to here is always belongs to here. So the next one will be from negative infinity up to.
Sorry, Professor, isn't it negative 1?
Which one?
Negative 1 over n.
Okay. Sorry, yeah, correct. Yeah. Then I have to redraw my picture. Okay, thanks. Then I have to redraw my picture. Yep. So minus 1 over n. So this is minus 1 including. So then minus 0.5. This is a minus 0.33. Okay, so this one. So first we have infinity up to minus 1. Maybe here, bigger one. Minus 1. 0 is here. Okay, so first of all, it's only up to here, right? Next, it's negative infinity up to 0.5, so which is up to here, including 0.5. And next, from negative infinity up to negative 0.33. So, however, it's never reached 0. 0 is not included. 0 is not included here. So you can see this line will be getting closer and closer to 0, but never touch 0. Right? You can see this. Maybe I draw this line here. Okay. So this end will getting closer and closer, but never touch this line. Okay. So you can see it will never include 0. So that's why you will get the answer will be negative infinity up to 0. So that's the idea how it can see. So it will closer and closer to 0, but never reach 0. Okay, that's the thing for that. Okay, so what is this actually? Oh, okay. This is the example. I missed this one. So this is another symbol. So given a set omega, so let's say omega is a set. So the power set of omega. So this is a so-called power set of omega. We're going to use this notation, script P of omega. So this is the class of all subset of omega. Okay, so this is an example. So let's say your omega consists of 3 objects, 1, 2, 3. Then the power set of this, you just list out all the subset. Empty set is one of the subset of omega. So that means empty set, the set with only one element, 1, 2, 3. Okay, and then the set with 2 elements, 1, 2, 1, 3, and then the set of 2, 3 as well, and the set of 3 elements. So this is the minimum power set. Okay, so when omega is finite, so we can always list out all the elements of P omega. So when omega is infinite set, so then it's impossible for us to list out all of them. Yeah, we can only describe it. Yeah. Okay, next one will be this important function is so-called indicator function. So it's a function which defines from a given set omega to 0, 1. So 1a omega is 0 when omega when omega does not belong to a, 1 omega belongs to a. So in a way, you can say this is sort of like a switch function. Okay. Okay, switch function. Oh, I think it's not right. So in a way, you can say this 1a is something like a switch function. Okay, so when omega belongs to a, so that means it's sort of like you switch on. So the value will be equals to 1. So when omega is not in a, so then you switch it off. So the value will return 0. Okay, so that's the way for it. So if you want to a very simple example. So let's say you look at a is this 0 to 1, okay, excluding the 2 endpoint, and then 5 to 10, including 10. So how's the graph looks like? So if you look at y is equal to 1a, okay, then you can see the graph will be like this. So you look at here, so 0 to 1, and then 5 to 10, right? Okay, so these two are the interval. So you can see whenever your omega belongs to this interval, the value returns 1. So that's why here. This is open, right? So exclude. And then, so all the value here will be 0. And this will be 0 and 0. Okay, next. From 5 to 10, it returns value 1. So exclude 5, however, include 10. So that's the value. Okay, so it's sort of like here, if you in this portions, you switch off. Okay, off it. Here, off. And then you switch on. So it returns the value 1. Okay, it depends on how's the shape of your A. Okay, then you have things like that. So this is what we so-called indicator functions. Okay, we're going to use it quite often in our course later. Okay, we have these properties for the indicator functions. Okay, forget about the infimum and supremum at the moment. Just look at this one first. Okay, okay. First of maybe this one is easy. If A subset to B, then 1A always less equal to 1B. Okay, 1A plus 1A complement is always equals to returns value 1. The indicator function of A and B is equals to indicator function A times indicator function of B. So to verify this four formula is quite strict, easy. We can actually do it using the table. Okay. So for example, we just look at it. We verify. I'm just show you the first one. One in theorem 0.24. Okay. So we want to verify the indicator function one of a and b is 1a multiplying 1b. So like I say, since this is sort of like a switch function, we take off and on properties, so we can actually use a table to verify it. Okay, so what we can do is, okay, we can look at this property. So look at the omega. We want to verify this, right? So that means what we need to do, we want to verify 1a and b of omega always equals to 1a omega multiplied 1b omega. For all omega belongs to the domain. We just need to verify the left-hand side equals the right-hand side. Okay, what we can do is we can actually use a table to do it. Let's look at it. So since we involve omega and involve two set A, B, right? So that means we look at these two behaviors. So omega belongs to A, omega belongs to B. Okay, also, we can see omega belongs to A and B. And then what is 1 in? Oh, I'm running out of space. Okay. I need all together. Okay, put a smaller one. Omega belongs to A, omega belongs to B. Okay, maybe I borrow a little bit space from here. 1 A omega multiplying 1 B omega. Okay, so omega belongs to A, omega belongs to B. So we have four different cases. So either first, omega belongs to A and omega in B as well. Omega in A, but omega does not in B. Omega not in A, in B, not in A, and not in B. Okay. So if omega in A, omega in B, so omega must be in A and B. So then we have not. Easy. So because of this is a switch function, omega in A, so these two we're going to switch on, right? On, off, or here. So this one is on, off, on, off, on, off, on, off. Okay. Okay, so this corresponding to this. So this is on, off, off, off. So we're going to have 1, 0, 0, 0. Okay, maybe just to let you know, I'm going to use a green color so that you can see the ratio. Okay, next, you just multiply 1 times 1. So we're going to have 1. 1 times 0, we got 0. 0 times 1, we got 0. This one 0. Okay, so we multiply, you will get this. Okay, you can see these two are identical. Right? Both give you the value, returns value 1, 0, 0, 0. Okay, so that's why these two are the same. So that's the way to verify it. Okay, maybe I'll give you a smaller picture. Okay. So this is how we can verify it. Okay. Then these two are the same now. Okay. So then we have verified. So hence 1A and B omega is equal to 1A omega multiplied 1B omega for any omega. So we have got this. So the rest you can actually verify on yourself. Okay, so it's not difficult. Okay, please remember this is an important formula. So I think we're going to use it quite often. Okay, in the remaining chapter. Okay, this is the one. So this is something about set theory. Most of the important properties of set theory. Okay, next we proceed to this. We are talking about the sequence of numbers. Okay, so we're going to discuss two different kinds of sequence. So first of all, we look at a sequence of number. So roughly speaking, a sequence is like that. So we're going to have a object, one object, we can two object, three, and so on. Okay, so that means a sequence is something that we can always list out all the object one by one. So as you can see, the object here could be numbers or other things. Like set. Okay. So it could be numbers or it could be other things like set. Okay. So here we talk about the first case, that is we just look at a sequence of number. I believe you should have already seen this in calculus. Okay, a sequence of numbers. Okay, so sequence of number. So we can have an example. Sequence of number. Sequence of number. So we can have, for example, we can have xk is equal to 2 over k. So then we're going to have 2 over 1, 2 over 2, 2 over 3, 2 over 4, and so on. Okay, so this is an example of sequence of number. Okay, when we have this, then we have four concepts here. First, infimum. Okay, it could with this minimum. Maybe we look at these two first. What's the difference? Okay, infimum is the greatest lower bound. So you look at all the lower bounds and then you identify the largest one. Okay, so this is minimum is the infimum, which is also an element of S. So you can put it in this way. So put it in this way, infimum is sort of like how should I say it? The eldest among your brothers, sisters, and how to write cursor now? My English rusted today. How to write cursor? C-O-U-R-S-I-N, right? So the eldest among all your brother, sister, and cousin as well. Okay, so inclusive someone which is not inside your family. You can put it this way, okay? So minimum. Okay, so this is the eldest among all your brothers and sisters. So this one must be in the same in the family. Okay, must be one of the member of your family. Something like that. Okay. Can I say this? Yeah. Okay. So you can put in this way. So similarly, then you can have supremum. Supremum is sort of like eldest among. Sorry, I should say eldest among all your younger brothers and sisters. Yeah. You have all the brother sister that is younger than you, and then you see who is the eldest one, including your cousin. Minimum is you look at among all your brother sister that is younger than you, then you see the eldest one. Okay, you have to exclude the cousin. That's the thing for it. Yeah. So similarly, you have a supremum and maximum. Okay, supremum is all the eldest, and then you find the youngest. The least upper bound. Maximum will be the supremum, but which is also an element of S. Okay, so that's the way for it. So the easiest way will be like this. You identify the infimum, and then you make sure which is also an element. Okay, which is also an element inside. Okay, so which is also an element. So infimum, and which is also an element, so that will be a minimum. Okay, that's the way. So that's the way. So when S is unbounded above below, so we put a negative infinity to be the infimum. When unbounded above, the supremum will be infinity. So let's look at this example. So I filled out answer in your lecture note, but just leave it blank just to demonstrate idea how to do it. Okay, so for example, you look at S. S is a set consists of only 3 elements here. So you look at here, which one is the infimum? So you can see 1 will be the infimum, right? So because it's always smaller than the other one. And 1 is inside, so 1 is also minimum. Okay, the reason is 1 is inside. One is inside S. Okay, this is not. I think maybe I can zoom a bit. Okay, 1 is an element of S, so we can accept. So in this case, 7 is larger, right? So 7 is a supremum, and also 7 is an element of S, so 7 is the maximum. Okay, so now look at this example, 1142. So you can see 11 will be the smallest one, right? So that will be infimum, will be 11. And also 11 is inside S. So 11 is the minimum. So similarly, 42 will be the supremum. Okay, but 42 does not belong to it. So we do not have maximum for this case. So this one, I think if you look at here, it seems to be clear. So 0 will be the infimum, and 9 will be the supremum. Okay, so 2 is not. Okay, you look at the largest and the smallest. Okay, so you can see 0 is infimum, but 0 does not belong to here. This is open, so we do not have minimum for this case, and we do not have maximum for this case. 9 does not include inside. Okay, N is the set consists of 1, 2, 3, 4, 5, and so on. Okay, so if you look at here, there's no N thing here, so which means the supremum will be infinity. And infinity is not a number. Okay, infinity is not a number, so please take note of it. Infinity is not a number, okay, which is just a symbol, which is a further away. So this is not a number, so therefore this one does not belongs to, it's not a natural number, so there is no maximum. So 1 is the smallest and also inside. Okay, 1 is an infimum. Okay, what is a Z? -2, -1, 0, 1, and so on. So you see that.
Sorry, doctor.
Yep.
I just want to ask the maximum we cannot write as infinity also.
No, because if you look at the idea. Okay, you look at minimum. Minimum say it is an infimum, which is also an element of S. Maximum of S is a supremum, which is also an element of S. Okay, element. So it have to be an element of S, right? Same as minimum. So as I said, infinity is not a number. N is a set of all natural number. Okay, this is all natural number. All natural number. So that means all the element for it must be a number. So infinity does not belong to here. Okay, so that's why you can see infinity is not a number. So then you can see that's why infinity, how should I say, no place to write. So this one is not an element for N. Get it? And also infinity cannot be element of Z, which is not an integer. Okay, I hope you get this picture. Okay.
Okay, good.
So this is very important. This is infinity is not a number. So that's why in this case, I think it's similar. Supremum must be infinity. Oh, time's fly. So okay, we have 5 minutes left. Make it quick. So this is minus infinity. So we have these two things. Okay. Okay, how about this one? 1/n. So maybe we need to look at this part. Okay, so just to let you get an idea. So if you look at S is 1/n, n is an integer. So that means this is like a, again, I think I put it in this way better. So 1/2, 1/3, 1/4, 1/5, 1/6, and so on. Just to let you see the picture. So I think it's clear, right? In this case, which one is the max? 1 is the maximum and minimum. I think in this case it's quite clear. I hope it's clear now. So in this case, supremum for this will be 8. Sorry, not 8. 1. Okay, 1 is inside. 1 must be a maximum. Got it? So if you look at here, if you look at the line, if you put a line here, so this is 1, this is 0. First we 1, and then half. Half becomes where is it? 0.33 somewhere. I don't know where is it. Okay, somewhere here. 1/3 and 1/4, 1/5, 1/6, 1/7, 1/9. But it never touched 0, right? It never touched 0, but it very close to 0. So from here you can see 0 will be a infimum. I hope you can get a picture. Okay, it cannot go beyond 0, and it never reached 0, so there is no minimum. Okay. In fact, I think it's quite straightforward. You can just look at the limit for it. So 7, 10. Okay, so maybe let us stop here. Okay, so it's about 7:30 already. So we stop here. As I propose, we take a break for half an hour. Okay, so you guys can have your lunch or go to do a praying section. Okay, then we carry on our second section for lecture in 8 o'clock. Right. Before that, you have any questions? Okay, so maybe let me answer this question first. Sorry, I can't see. Okay, Ima. So the question is the assignment will be individual or in group? So the assignment is individual. Okay. No group assignment. So any other questions before the break? Great. I suppose no. Okay, so let's take a break. So we carry on our lecture on 8 o'clock, right? Okay, see you guys.